Hey, good afternoon. My name is Justin Bro with Argonne National Laboratory. I work in the Communications and Public Affairs Office at Argonne. We essentially communicate the scientists' ideas to the external world. Today we're going to talk about a really exciting subject. Recently, AT&T partnered with Argonne climate and infrastructure scientists on a climate resiliency project. So today we're going to take a little time to talk to some of the experts that are intimately connected with that project. I'm going to start up with our gentleman over here to my left. This is Tom Wall. How you doing, Tom?
Good. How are you?
I'm doing well. Why don't you explain to our audience here who you are and what you do for Argonne?
Sure. So my name is Tom Wall. I'm a senior infrastructure and preparedness analyst here at Argonne in our Decision and Infrastructure Sciences division. I'm a civil engineer by training. I work on large-scale infrastructure projects to assess vulnerabilities and try and promote resilience in these large-scale infrastructure systems.
Thank you so much. So Argonne is working with AT&T on a climate resiliency project. That's correct?
Yep.
Okay.
Yep.
And that's going to help AT&T better anticipate, prepare for, and adapt to the impacts of climate change and extreme weather events for the company's infrastructure. So my first question for you, Tom, is how did this project come about?
Yeah. No, that's a great question. So it's funny. It's like a lot of things. It was a conversation where one of our coworkers was at a meeting for a completely separate project and engaged with some folks from AT&T. And they were just sort of talking about different ideas and different concerns that the company has. And climate was one that sort of rose to the top over the course of that conversation and through a number of follow-up conversations. So, we connected our people with certain people in their organization, and slowly this project built out of that.
Okay, and I want to talk a little bit more about that project, and let me advance the slide over here if you want to hit that right button. So this essentially is the area that you were helping out AT&T with, is that correct?
Yep. So they were particularly concerned about climate impacts in the southeast United States. And so the project that we did looked at both North Carolina and South Carolina, and then Florida and Georgia.
Okay. So my next question for you is, okay, weather events and extreme climate pose a significant threat to U.S. infrastructure systems. I think we all know that climate change is what's happening. What do we mean by infrastructure, though?
Yeah, so infrastructure is really just the built environment, the built systems that support societies, support communities, and support civilization. So things like things like power lines, like the power grids, is a great example of infrastructure. Highways and the transportation system, so roads, rail systems, airports, seaports. Also things like water systems, water and wastewater. So when you flush the toilet or when you turn on the tap in your house, that's all part of this larger infrastructure system, and it's all vulnerable to different types of climate impacts. So, for example, here on the left, we've got a picture of some downed power lines. That could have been from a hurricane, from a tornado, from a big storm or high winds that cause damage to this infrastructure system.
Okay. And so we're not just talking about, we're talking about basically everything that we've come to know to live in a modern society. We're talking about health, right? We're talking about hospitals.
Absolutely.
We're talking about how we get our energy. We're talking about power lines. We're talking about clean water, all these infrastructure. This is what infrastructure consists of.
Yep. It's the things that allow you to go through your normal day and support your daily life.
Perfect. So my last question for you, Tom, is AT&T is using these insights from Argonne to develop a climate change analysis tool. And the company is piloting the tool in the southeastern region of the United States. If we can go right back to the previous slide right there. Again, I just want to remind our viewers, this is the area that Argonne and AT&T worked with on this climate change analysis tool. And it's been particularly, that area has been particularly hard hit by severe weather and hurricane in recent years. In addition, AT&T will be making the climate data available to the public, universities, municipalities, and others to use in their own climate risk analyses, which has the potential to benefit whole communities. So my last question for you, Tom, is what expertise does Argonne bring to the table, and how far in the future are we talking about as an assessment?
Sure. So let me answer the last part of your question first. So, our climate models look out to the mid-century, so 2050, 2060. So we're looking, roughly about 30 years into the future. So what could the climate look like that could affect these infrastructure systems by mid-century? And what's unique about Argonne is we've got a lot of different and diverse capabilities here. So I'm gonna fast forward to this slide because this really illustrates the different types of people and expertise that come together to solve these types of complicated problems. So, we've got climate scientists. These are the folks that are projecting climate out to mid-century, but all of this is based upon climate modeling. And all of these models require computer scientists and also massive computing resources, supercomputers like we have here at Argonne. But it also requires people like me, people, engineers, to see how these types of climate impacts will affect infrastructure in the built environment. And we also have statisticians and hydrologists and environmental modelers who can take these types of climate impacts and really translate them into what happens at the local level that's affecting infrastructure.
Okay, and so what I'm hearing right now is essentially it's a team effort. You're not just doing it by yourself.
That's right. This project would not be a success at all if we didn't have a diverse team of people with different expertise, working together here in one organization at Argonne to really move this work forward.
Thank you so much. I appreciate it.
Yeah, thank you.
We're going to leave our conversation with Tom here, but we've been talking a little bit about the climate change and what Argonne offers insofar as capabilities. And if you want to look right back at this slide, I just want to show people one more time. It's not just a one-person deal, right? You have a number of people working together from different specialties to be able to get to an assessment. And again, we're talking about, as Tom mentioned, mid-century. We're talking about until the year 2050 insofar as what are the impacts of climate change on particular infrastructure. To forward this conversation, I want to come over here and talk to Cristina Negri, who is the Division Director of the Environmental Systems Division over here at Argonne. How are you doing, Cristina?
Very well, thank you.
Excellent. Okay, so my first question for you is, I got to get my paper ready. I don't memorize everything. My first question for you is, who funds this work?
Well, great question from you, Justin. Obviously, the work we've been doing now, and we are talking about the AT&T work, has been funded by AT&T. They're really interested in a very specific problem, estimating the uncertainty, understanding what are their exposure as far as risk to climate in a specific region. However, we wouldn't be able to do that work. We would have been able to do that work if we hadn't had years and years of funding from other agencies that are really more interested in the more fundamental questions regarding climate. For example, the Department of Energy has helped us a lot, has provided us the funding to understand the very fundamental questions about how climate forms and how weather forms, particularly things like how do clouds form? What makes clouds, become clouds? Or what is the energy how does the energy that comes from the sun get dissipated through the atmosphere and things like that, right? In addition, Department of Energy provides the supercomputers, and the computers are necessary to actually run this very, very data-intensive and calculation-intensive type of work. Additionally, other organizations like the Department of Defense has really helped us and funded us to do physics-based regional modeling that can take models that are designed for global estimations and understanding down to more focused areas and what we call downscale, meaning smaller areas but with a lot more data. So it's a really joint effort, but basically the fundamental science is really Department of Energy and the government, and the specific applications go back to industry because each one has different needs.
So we're talking about what we just talked about with the specific needs of industry. So if you look at this infographic, that's where we're here. This is what DOE funds in particular. This is what DOD. Again, what I'm hearing is this is a team sport.
Absolutely.
Multiple organizations getting together, and particular organizations have certain applications, but the fundamentals are here.
Yeah.
The fundamentals are here.
Exactly, and those complement each other pretty well.
So my next question for you is, what are some of the things we specialize, Argonne in particular specializes in, and how do we create partnerships within Argonne to solve those complex problems?
Okay. That's a good question. I think I'll go back to what my colleague Tom said before, and I bring up the same slide because it's really what we want to talk. Argonne is special in that sense. If you think research, oftentimes you think academia. We are quite different from that in the sense that we are driven by a mission, the mission of the Department of Energy. And so you have at the ready a number of people that are thinking the same way, we are thinking the same problem over from different angles. And so at the drop of a hat, if you will, we are really ready and primed to actually address these mission critical work such as climate is, right? And so we have hydrologists. I myself am an agronomist, so I specialize in crops and environment. Climate scientists, computer scientists, sociologists, engineers, statisticians, and many others that really get together and form these connections across each other. And obviously we all work together on the same organization, and so it's easy for us to form these team-oriented work and proceed with what we need to investigate.
That's amazing. So one question I do have for you. So when I wake up in the morning, the first thing I do is turn on the news, right? I think everybody does that.
Right.
Unless they did get the coffee first. Either they get the coffee first and turn on the news or vice versa. Either way, when I turn on the news, I'm seeing things about the weather. So my local forecaster is talking about it's going to be 46 degrees today, and tomorrow it's going to be 56. But that's gotten me to thinking, we're talking about climate, but when I wake up in the morning, I'm watching a weather forecast. What's the difference between weather and climate?
Okay, well, that's a great question. I think we all have, at one point in our life, really struggled with this, right? And as models become more powerful, the two will become even more confused or overlapping. But think about this: a weather model. So first of all, both weather and climate models are based on physics, right? So the fundamental science that we learned DOE funds us to do is the science that really underpins both these models. But they're constructed different ways because they're really trying to answer different questions, right? So the weather, what you need to do for weather is like, what am I going to wear today or tomorrow, right? So it's very short term and very oriented towards, is it going to rain? Is it going to be cold, warm? Or is it going to be a pleasant day, or how do I prepare for the day, right? Climate, on the other side, takes, as Tom was saying, the view of like 30 years on, right? So longer things. So if you think of it as really more of an aggregate, an averaged out impact that you're looking at, or what is going to happen in like 30 years. So it's a different scale. And a little bit is similar to what type of clothes do you have in your closet, right? Do you live in the tropics? Do you live where you live? Is it summer? Is it winter? So it's longer. It's not day to day. It's a little longer than that. And if you imagine the same concept for the organization that need to decide what to do and make significant investments in infrastructure, for example, that really a climate model is the one that is going to tell them, what can you expect? How can you intensify weather events? Can you think of increases in temperature? So what will be the need for climate controls, or for heating, or for air conditioning, and going forward? So informs a broader set of stakeholders really that are not just looking at what's happening today and tomorrow, but longer term.
And when I'm thinking, as you're talking, so if I'm thinking about weather, and I'm trying to build the analogy in my own head, so what you're doing is essentially taking today, April 1st, you're going to look at April 1st last year, the year before, the year before, the year before. Is that going to go into your assessment for what's going to happen 30 years in the future?
Well, somewhat, but then it's combined also with what we know of what makes weather, right? So it's more, it's not just statistics. There's a lot of physics involved in that.
Right. Thank you. That's the fabulous part of the conversation. Can't wait to come back to it. Okay, so that was Cristina Negri, and she is the Division Director of the Environmental Sciences Division. But this has really got me jazzed about the science behind these things that we're talking about. And we have someone else to talk to, who is Kotamarthi, and he's Chief Scientist and Department Head of Atmospheric Science and Climate with the Environmental Science Division. How you doing there, Rao?
Good, good.
Good to see you again.
Yep.
All right. So, again, I have a little piece to read to you here. The Southeast Regional Climate Center has historical data about hurricanes and tropical storms that have affected the Southeast region. So if you remember the map that we were looking at before, the Southeast region of the United States, this is the hardest hit area of the region of the United States. My first question for you, Rao, is what is the history of extreme weather in the Southeast region? And in a larger context, if we zoom out to a 150,000-foot scale, what do we expect to see in the future?
Yep. Let me just change that. Just like, so the Southeast United States has experienced about 300 hurricanes from starting 1850 to now. So it's, on average, you have about 2 hurricanes per year, and that's been kind of consistent over the last 150, 170 years. So of all the hurricanes that occurred there, Florida has about 40% of the hurricanes, which is amazing. 40% of the 300 actually landed in Florida.
Yeah, let me say that again. So 40% of all the hurricanes that have happened in the last 150 years?
Last 150, 170 years now.
On Florida?
40% of
40%, right, okay.
Or the North Atlantic, which is amazing if you think about
yes,
it.
That's a lot.
So that's why that makes the Southeast very, very interesting in general. And of course, a lot of the infrastructure there is vulnerable to hurricanes. So that happens to be one of the biggest concerns there. And as we go into the future, we can think of climate change models, as we talked before, and what they're projecting, right? It is a kind of an evolving science right now. There's a lot of challenges in actually modeling a hurricane. climate models, as you know, run on a really, really large grid. What I mean by that is that each point in a climate model, when I kind of think of a pixel map, each pixel is about 100 kilometers.
Okay.
So 100 kilometers by 100 kilometers, you're talking 10,000 square kilometers. So because it's so big, the hurricanes are much smaller than the grid size of this. So they cannot actually capture them very well. But you can still try to get statistics out of them. What they indicate right now is that on average, or look at all the models, there are about 30 to 40 models around the globe that do global climate. It seems like maybe the number of hurricanes will not change, but the intensity could be changing in the future. So you may get a higher intensity hurricane. There are other models like the ones we use, which can go to really small scale. Which can go to a really small scale, like 4 kilometers and 12 kilometers. So, but unfortunately, it's so expensive to run them. We don't have enough data from them to actually understand what they're projecting.
What are we seeing here?
So this is Hurricane Matthew that we model actually for the AT&T project. It shows the flooding as the event progresses along the southeast. South Carolina, Charleston got affected quite a bit. So the Matthew is one of the big hurricanes over there in the southeast for the last decade, I guess. So this was actually done with a really high resolution model. With the model actually, some of these calculations, the grid size was it's a coastal flooding model that was used for this called EarthCert, and the grid sizes get as low as 10 meters. So the reason you want.
Hold on a second. You were just talking about hundreds of kilometers.
Yeah.
So you're talking about now going from hundreds of kilometers to 10 meters?
10 meters. Okay. And the reason you want to get 10 meters or at that scale is that, as you can imagine, the water goes through the inlet. I mean, the small inlets are the ones where all the water rushes through. So you want to resolve that in a model. So this particular model, the resolution we ran for this southeast actually was able to resolve those things.
That's amazing.
So we use this for the current climate. We also did for the future in the mid-century situation for this, because we have a model that actually simulates the atmosphere for most of the North Atlantic. So we use that to drive this EarthCert model to do some projections into the future.
Okay, I want to continue our question here. So if we go to the next slide, we're talking more about statistics and data, and I think this is where we're getting into, again, the work that Argonne was doing with AT&T in the southeast region to help AT&T basically shore up, understand like what the issues of climate change impacts would be in the future for their area. So let me ask you this: what types of data and/or statistics are you working with?
So the biggest statistic that everybody who lives there is interested in is what is going to happen to the intensity of the storm, and
is it going to get stronger?
Stronger, or it's going to get weaker? And that is a interesting question, very tough question to answer. And when we're talking to AT&T, the thing that they are most interested in terms of intensity is flooding. What will happen? How deep is the flood going to be?
Because they have infrastructure along
the
coast,
and most of the regions there. And the second thing they were interested in is wind. How strong is the intensity of the wind going to change in the future? So once we identified those two things, we started doing calculations for both flooding, inland flooding, which is basically means inside the coast. So the coastal model only goes up to where the elevation changes about 10 meters.
Okay.
After that, you really don't need a coastal model. If the water from the ocean is coming over 10 meters, there's a problem.
Right.
There's a bigger problem.
Right.
So, so once you go beyond that, then we use an inland flood model to actually simulate that. So there are two different flood models used there. And in addition to that, we have run a whole North American simulation for the atmosphere. So using that, we can actually calculate wind extremes in wind.
Okay.
So these two things are the ones we did. And the cool thing, the one that I'm really excited about is that we reduced this the whole data set for this project is about 1 petabyte. It's a massive amount of data.
Let's so for people who don't know what a petabyte is, try to explain what a petabyte is.
Oh God.
You brought up the word, yeah.
Well, let's say a DVD is probably 5 gigabytes.
Okay.
So I imagine 500,000 DVDs.
500,000 DVDs, approximately
5 million, maybe even bigger,
equals a terabyte, which is the data, a petabyte, the data that you were working with.
Yeah.
That's a lot of information.
I probably have made a mistake with a zero,
That's
but
right.
it could be bigger than
It's
that.
live TV.
So what we did is we actually developed a simple, I wouldn't say simple, a statistical distribution of the events that we can fit with just three parameters. So each of the cells, the data we gave to AT&T is actually at a resolution of 200 meters.
Okay.
So it's fairly small. Each 200 meter cell, you can go and use this distribution to see how the maximum flood you see in this place will change from now to future 50 years. So, and the uncertainty associated with that. So
Perfect.
that's the coolest thing we did. So we reduced all the data into something like 500 megabytes by using this.
That's a lot of movies.
Yes, that's a lot of movies.
As we're moving on, if you don't mind advancing the slide over there. So given the information that we know about modeling and the role that statistics plays, from that, what do we know about how climate change affects different regions? And I pulled up this image, and this is a NOAA region, and thank you, NOAA, for providing such amazing graphics for us. But this is just one example of how there are different effects in different parts of the country. So if I get this correctly, climate change doesn't happen the same everywhere.
Yep, that's correct. That's one other big thing to realize, that it's not going to be uniformly 5 degrees increase all over U.S.
Okay.
It's going to be different. So as we discussed before, in the southeast, the biggest concern may be what happens to intensity of flooding, because the intensity of rainfall over that region is changing as you go into the future. But if you go into the west, along the west coast, the thing that is happening is that the number of days. One of the interesting things we see in our simulations is that if you look at the 95th percentile and above temperatures, that means the top 5% of temperature you see in the climate right now over the west, will be the number of days that see them will be more than 2 to 3 times than we are seeing right now. So the number of hot, really hot days over the southwest is going to be triple of what you are seeing.
In that particular region,
yes,
that's typical for that region. We're just going to have more of them.
Yes,
Okay.
it's going to be more of it. So that's the interesting changes that you see as you go across the country.
I wanted to move forward because this is, so what we saw before, so this is 2017 data. This is happening this year, and this is the spring flood outlook. I don't know if you want to talk a little bit about that.
I mean,
we've had some pretty bad floods in the Midwest.
Yes, this year has been particularly interesting in the sense that the number of flood events that took place in Nebraska, for example, where they have not seen floods like this in quite a while. And whether this is due to climate change or weather is hard to say at this point because it's happening right now.
Right.
What contribution climate makes to these kinds of events is one of the big things that scientists are trying to solve. There are ways of doing that, so we call it attribution. So we are trying to attribute what percentage of this change is actually due to climate change and what is natural variability. So that's one of the big challenges as we go forward.
And I want to go forward because you have basically a really beautiful simulation or visualization of the flooding of an area. So if you look here, you want to explain that just a little bit about what's happening on this graphic?
So this simulation shows the coastal flooding happening, and this is, I think, this was in Maine. This is a city in Maine. So it shows the water depth increasing as you go on. So about a 30-year simulation.
Okay. All right, so we're going to head back over to Cristina. Thank you so much, Ralph, for that. That's what I'm talking about. We're going to head back over to Cristina right now. Because one of the questions that we have is, so, okay, we're having some technical difficulties, so stay with me really quickly. But what I wanted to talk to Cristina a little bit about is that the fact that AT&T and Argonne work together on this particular project. To me, that means that other organizations have the capability or have the ability to work with Argonne on certain projects. So one of my first questions for you is, what types of industries should contact you for work like this, and why?
Well, the reason for organizations to work with us is really to better plan for their investments or understand what their exposure could be to some of the events that Rao has mentioned. Right, so anybody, any organization that has interest in, has land deployments, whether it's infrastructure, as Tom was saying, urban systems, we think of stormwater when you think of flooding, in Chicago we are very familiar with, sewer backups, and although the district has been doing a lot of work in mitigating those, but still these are concerned, and there is limits to engineering, right, to what has been planned for the last 100 years and how to bring it forward. Utilities is another one. Federal, local governments, people who are involved in emergency management, try to have a little more understanding what could happen and how to better plan. Telecommunications, oil and gas, reinsurance, and insurance industry, generally speaking, and federal, local government, as I said, and agriculture. As we've seen now in the Midwest what the floods are, and really having a better outlook on what kind of impacts to crops and cropping systems could have. That could be also a good
Perfect.
right.
And so all these organizations and more that aren't simply listed here, they can come to Argonne and they can talk with Argonne scientists. And as we talk with you and with Tom and with Rao, it's really a team approach, right? So we're talking about climate scientists, we're talking about people that work on supercomputers and all these types of things. So you get an all-in approach to finding out what are going to be the potential impacts going forward, say 30 years, for your particular infrastructure. Particularly, especially we talk about foodstuffs, right? We're talking about agriculture.
Critical, yeah.
What type of food are we going to be growing in 30 years, right? So very, very important. So then my next question becomes, if these types of organizations and more can work with you, how do they get in contact with you?
Well, they can get in touch with you, but more broadly, partners@anl.gov is really our general address where people are there at the ready to answer people's questions and find ways to collaborate with us in the best way possible.
That's perfect. Thank you so much, Cristina.
Thank you. Thank you very much.
All right, so we're going to wrap it up today, but I want to say thank you to Cristina Negri. I want to say thank you to Tom Wall. I want to say thank you to Rao Kotamarthi. Today we were talking about Argonne's work with AT&T to help them shore up their infrastructure for the next 30 years. There's a team of scientists, an all-in approach to help organizations, large and small, figure out what's going to be impacting their infrastructure over the next 30 years. Continue the conversation. We will. Thank you so much for joining us.